Introduction. The first requirement for remote sensing is to have an energy source to illuminate the target unless the sensed energy is being emitted by the target. This energy is in the form of electromagnetic radiation. All electromagnetic radiation has fundamental properties and behaves in a predictable ways according to the basics of wave theory. In this chapter, we will discuss about electromagnetic spectrum, wavelength, regions important for remote sensing, electromagnetic radiation qualities, interaction mechanisms, wave theory and particulate theory, Stefen Boltzmann law, Weins displacement law. Electromagnetic radiation consists of an electric field which varies in magnitude in a direction perpendicular to the direction in which the radiation is travelling, and a magnetic field oriented at right angles to the electric field. Both these fields travel at the speed of the light. Two characteristics of electromagnetic radiation are particularly important to understand remote sensing. These are the wavelength and frequency. Wavelength is the two adjacent identical points, that is, it might be an adjacent crust or adjacent trough in the adjacent cycles of the wave from signal propagated in space. Frequency is a number of waves passing through a single point in a unit time period. Electromagnetic radiation plays a major role in remote sensing systems as it is a vital signal which is absorption or reflected by the object or the surface which is captured by the sensors, which preferred is to be processed and studied under various categories. As the technology has improved, we are about to understand more about the different spectral wavelength of electromagnetic spectrum, and we are able to use these radiations. Various fields of science. Electromagnetic radiation as an electromagnetic wave that travels through the space at a speed of a light, which is 3 into 10 to the power of 8 meters per second. Theoretical model of random media including the anisotropic effects, random distribution, discrete scatters, rough surface effects have been studied for the remote sensing with electromagnetic waves. Light can be thought of a wave in the electromagnetic field of the universe. The wavelength is the length of one cycle, which can be measured as the distance between the successive wave crust. The wavelength is usually represented by the Greek letter lambda. Wavelength is measured in meters or some factor of meters such as nanometers, that is 10 to the power of minus 9 meters, or micrometers, that is 10 to the power of minus 6 meters, or centimeters. Frequency refers to the number of cycles of wave passing a fixed point per unit time. Frequency is normally measured in hertz, equivalent to 1 cycle per second and various multiples of hertz. Therefore, the two are inversely related to each other. The shorter the wavelength, the higher the frequency. The longer the wavelength, the lower the frequency. Understanding the characteristics of electromagnetic radiation in terms of the wavelength and frequency is crucial to understand the information to be extracted from the remotely sensing data. The electromagnetic spectrum ranges from a shorter wavelength including gamma and X-rays to the longer wavelengths including microwaves and broadcast radio waves. There are several regions of electromagnetic spectrum which are useful for remote sensing. In the given image, you can see what is a wavelength, how many different types of waves are present in the electromagnetic spectrum. Wavelength regions important for remote sensing: ultraviolet or UV. For the most purposes, ultraviolet or UV of the spectrum, shortest wavelength, are practical for remote sensing. This wavelength is beyond the violet portion of the visible wavelength, hence its name. Some earth surface materials, primarily rocks and materials, emit visible radiation when illuminated by UV radiation. Visible spectrum. The light which our eyes, that are remote sensors, can detect is a part of a visible spectrum. It is important to recognize how small the visible portion is relative to the rest of the spectrum. There are a lot of radiation around us which is invisible to our eyes, but can be detected by other remote sensing instruments and used to our advantage. The visible wavelength covers a range from approximately 0.4 to 0.7 μm. The longest visible wavelength, that is red, and the shortest is violet. Common wavelength of what we perceive as a particular colors from a visible portion of the spectrum are listed. The important is to note that this only portion of the spectrum we can associate with the concept of colors. Violet 0.4 to 0.446 μm, blue 0.46 to 5, green 0.5 to 0.57, yellow 0.57 to 0.59, orange 0.59 to 0.62, red 0.62 to 0.7. Blue, green and red are the primary colors of the wavelength of the visible spectrum. They are defined as because no single primary colors can be created from the other two, but all other colors can be formed by combining blue, green and red in various proportions. Although we see sunlight as a uniform or homogeneous color, it is actually composed of various wavelengths of radiation in primarily ultraviolet, visible, infrared portions of the spectrum. The visible portion of this radiation can be shown as a components of colors. When sunlight is passed through a prism, which bends the light in different amounts according to the wavelength. Infrared. The next portion of the spectrum is the interest is the infrared region, which covers the wavelength range from approximately 0.7 μm to 100 μm, more than 100 times as wide as the visible portion. The infrared can be divided into three categories based on the radiation properties: the reflected, near infrared, middle infrared and thermal infrared. The reflected near infrared covers wavelength from approximately 0.7 μm to 1.3 μm. Is commonly used to expose black and white and color infrared sensitive film. The middle infrared regions include energy with a wavelength of 1.3 to 3 μm. The thermal IR region is quite different than the visible and reflected IR portions, as this energy is essential. The radiation that is emitted from the Earth's surface is in the form of heat. The thermal infrared covers wavelength from approximately 3 μm to 100 μm. Microwave. This wavelength or frequency interval in the electromagnetic spectrum is commonly referred to as a band, channel or region. The major subdivision of this portion of the spectrum of more recent interest to the remote sensing is the microwave region from about 1 mm to 1 meter. This covers the longest wavelength used for remote sensing. The shortest wavelength have properties similar to the thermal infrared region, while the longer wavelengths approach the wavelengths used for radio broadcast. Electromagnetic radiation qualities. Radiant energy is the energy carried by electromagnetic radiation. Radiant energy causes the detector element of the sensor to respond to electromagnetic radiation in some appropriate manner. Unit of radiant energy is joule. Radiant flux. Radiant flux is the time rate of the flow of the radiant energy. The unit of radiant flux is joule per second or volt. Irradiance. Irradiance is a radiant flux intercepted by a plane surface per unit area of the surface. It arrives at the surface from all the direction within the hemisphere over the surface. Unit of the irradiance is volts per meter square or volt meter square. Radiance. Radiance is defined as the radiant flux per unit solid angle leaving an extended source in a given direction per unit projected area of the source in that direction. The concept of radiance is intended to correspond to the concept of brightness. The projected area in the direction which makes an angle theta with the normal surface area is A cos theta. Unit of radiance is volt meter per second. Spectral reflectance. Spectral reflectance is the ratio of reflected energy to the incident energy as a function of the wavelength. Spectral signatures are the values of the spectral reflectance of the objects averaged over different well-defined wavelength intervals. Comprise the spectral signature of the object or the features by which they can be distinguished. Interaction mechanisms. A number of interactions are possible when electromagnetic energy encounters matter, whether solid, liquid or gases. The interaction that takes place at the surface of the substance are called surface phenomena. Penetration of electromagnetic radiation beneath the surface of the substance results in interaction called volume phenomena. The surface and volume interaction with matter can produce a number of changes in incident electromagnetic radiation, primarily changes of magnitude, direction, wavelength, polarization and phase. The science of remote sensing detects and records these changes. The resulting images and data are interpreted to identify remotely the characteristics of the matter that are produced the changes in the recorded electromagnetic radiation. The following interactions may occur. Radiation may be transmitted, that is, passed through the substance. The velocity of electromagnetic radiation changes as it is transmitted from air or vacuum into other substances. Radiation may be absorbed by the substance and give it up its energy largely to heating the substance. Radiation may be emitted by the substance as a function of its structure and temperature. All matter at temperatures above 0 degrees Kelvin emits energy. Radiation may be scattered, that is, deflected in all directions and lost ultimately to absorption or further scattering as light is scattered in the atmosphere. Radiation may be reflected. If it is returned unchanged from the surface of the substance with an equal angle, with the angle equal and opposite to the angle of incidence, it is termed the specular reflectance, as it in the mirror. If radiance is reflected equally in the all direction, it is termed as diffuse. Real materials lie somewhere in between. The interaction with any particular form of matter are selective with regard to the electromagnetic radiation and are specific for that form of matter, depending primarily upon its surface properties and atomic and molecular structure. Wave theory and particle theory. Light can exhibit both a wave theory and a particle theory at the same time. Much of the time, light behaves like a wave. Light waves are also called the electromagnetic waves because they are both made of electric and magnetic fields. Electromagnetic fields oscillate perpendicular to the direction of the wave travel and perpendicular to each other. Light waves are known as transverse waves as they oscillate in the direction transverse to the direction of the wave travel. Electromagnetic propagation. Waves have two important characteristics, wavelength and frequency. The sine wave is the fundamental waveform in nature. When dealing with the light wave, we refer the sine wave, the period t of the waveform is one full 0 to 360 degrees sweep. The relationship of frequency and the period is given by the equation f is equal to 1 by t, t is equal to 1 by f. The waveforms are always in the time domain and go on for infinity. The speed of a wave can be found by multiplying the two units together. The wave's speed is measured in the units of length, that is, wavelength into frequency is equal to speed. As proposed by Einstein, light is composed of photons, small packages of energy. The reason the photons are able to travel at light speed is due to the fact that they have no mass and therefore Einstein's infamous equation E is equal to mc square cannot be used. Another formula devised by Planck is used to describe the relationship between the photon energy and frequency. Planck's constant h is equal to 6.63 into 10 to the power of minus 34 joule per second. That is, E is equal to hf or E is equal to hc by lambda. E is the photonic energy in joules, h is a Planck's constant and f is the frequency in hertz. Particular theory. The basic idea of quantum theory is that the radiant energy is transmitted in invisible packets whose energy is given in integral parts of size hv, where h is a Planck's constant and v are photons. The dilemma of the simultaneous wave and particular waves of electromagnetic energy may be conceptually resolved by considering that energy is not supplied continuously throughout a wave, but rather it is carried by photons. The classic wave theory does not give the intensity of the energy at a point in a space, but gives the probability of finding a photon at that point. Thus, the classic concept of a wave yields to the idea that a wave simply describes the probability path for the motion of the individual protons. The particular importance of the quantum approach for remote sensing is that it provides the concept of discrete energy levels in materials. The value and arrangement of these levels are different for different materials. Information about a given material is thus available in electromagnetic radiation as a consequence of transitions between these energy levels. A transition to higher energy level is caused by the absorption of energy, or from a higher to a lower energy level is caused by emission of energy. The amount of energy either absorbed or emitted corresponds precisely to the energy difference between the two levels involved in the transition. Because the energy levels are different for each material, the amount of energy a particular substance can absorb or emit is different for that material from any other materials. Consequently, the position and the intensity of the bands in the spectrum of a given material are characteristic to that material. Stefen-Boltzmann law. Stefen-Boltzmann law, also known as Stefen's law, describes the power radiated from a black body in the terms of its temperature. Specifically, the Stefen-Boltzmann law states that the total energy radiated per unit surface area of a black body across all wavelengths per unit time is also known as black body radiant existent or emissive power, is directly proportional to the fourth power of the black body's thermodynamic temperature, T. Weins displacement law. Weins displacement law states that the black body curve for different temperature peaks at a wavelength inversely proportional to the temperature. The shift of that peak is direct consequence of the Planck's radiation law, which describes the spectral brightness of the black body radiation as a function of the wavelength at any given temperature. However, it had been discovered by the William Mean several years before Max Planck developed that more general equation and describes the entire shift of the spectrum of the black body radiation towards shorter wavelength as temperature increases. Formally, the Weins displacement law states that the spectral radiance of the black body radiation per unit wavelength peaks at the wavelength lambda max. Lambda max is equal to B by T, where T is the absolute temperature, that is in degrees of Kelvin. B is the constant of probability called Weins displacement constant, which is equal to 2 into 89 into 10 to the power of minus 3 mK, or more conveniently to obtain wavelength in microns. If one is considered the peak of black body emission per unit frequency or per proportional bandwidth, one must use a different proportionality constant. However, the form of the law remains the same. The peak wavelength is inversely proportional to the temperature, or the peak frequency is directly proportional to the temperature. Weins displacement law may be referred to as Weins law, a term which is also used for Weins approximation. Summary. The first requirement for remote sensing is to have energy source to illuminate the target unless the sensed energy is being emitted by the target. This energy is in the form of electromagnetic radiation. All electromagnetic radiation has fundamental properties and behaves in predictable ways according to the basis of wave theory. The electromagnetic radiation extends over a wide range of wavelength. The entire range of radiant energies is called electromagnetic spectrum. The electromagnetic radiation ranges from a very high energy radiation such as gamma rays and X-rays through ultraviolet light, visible light, infrared region and microwaves to radio waves. These divisions are ordered according to the frequency, wavelength or wave number. Our eyes are sensitive to only a small portion of electromagnetic spectrum called visible range. Radiations beyond the visible region are invisible to our human eyes, but can be detected by some remote sensing devices such as thermal sensors that can sense the radiation in the thermal infrared region. You should also note that the division of electromagnetic spectrum is for practical purpose. The gamma rays and X-rays are potentially dangerous, and also the ultraviolet light is powerful enough to cause sunburn. You can also feel the infrared radiation as heat. You know that we employ microwaves in microwave ovens and radio waves are used for communication. All types of electromagnetic radiation are waveforms which travel at speed of light. The radiation can be defined in terms of either their wavelength or frequency. Shorter wavelength radiations, example infrared or shorter, are generally described in the term of wavelength, whereas longer wavelength radiations like microwave, radio waves, etc. are generally described in the terms of its frequency.